So I guess just a comment or an observation from my experience is that clouds, or I should say clusters, are made usually out of commodity equipment, and commodity equipment tends to have a much higher failure rate than its HPC counterpart. So there seems to be a crossover point where the cloud actually costs you more money because it's constantly down, and the HPC system isn't. What's sort of your comments along those lines?
So there's a wonderful example where for the accelerator out in CERN, they actually store the data of one of the experiments using Hadoop or using HDFS. And the reason is because they couldn't get enough storage cheap enough for the project. So what they did was to buy lots and lots of disks and lots of machines, and they duplicated all of the output. HDFS worked very well for them, and this is how they actually managed to keep copies of what had happened in the experiment. Now, of course, the problem is they got all this data and they have to process it, but they did manage to collect the data that way.
And I think relevant to this university, I had the pleasure of using the LAC 4, and we managed to get a lot of time in LAC 4 because we wrote algorithms for 16 processors because you could never get it to work with 64. It had 64 machines, and it was a very lucky day when all of them ran perfectly. So we got time where codes were written for 64 that couldn't run. We would say, well, we'll run, and we got in under there because we were actually stealing time rather than getting allotted by grants. So one of the things as well that you need to be aware of is not only mean time to failure, but mean time to error. If you take an Intel CPU, and let's say you're doing something as simple as it's just going to use the cache and registers and do ALU, arithmetic operations, how long do you think you compute before you get an error where it says 2 + 2 = 5? You'll find it's embarrassingly short. Now, we had one process. I have to be nice because they're a partner of us, so I won't say the number of weeks, but it's an embarrassingly small number. So if you expect perfect computation, you're going to be sorely disappointed. So you need to build code that's adaptive and is fault tolerant. When I did my seminar on how to find a new largest known prime, I say expect 70% of the time to be checking errors and rechecking errors. You only think new problem 30% of the time. Now, Intel will say, when we showed them one of the chips and how bad it was, error rates, their response was, quote, Windows has a shorter mean time to error. We're not the weakest link, so don't bother us, right? So don't expect, so so these commodity hardware, and by the way, one of the things that happens, the cloud does to, HPC does to the cloud, is the cloud depends upon you running in a green environment. That is, they set the BIOS settings so that that it'll drop speed and try to be as green as possible, because part of the cloud economics you're talking about is over the issue of, or I guess that also gentleman is assuming that you're not consuming high power. When you drive it in HPC loads, you're much faster mean time to error, right? When you overclock it, then you can kiss your error rate goodbye in a bad way. So cloud providers are going to find, when HPC applications start running on them, that their economic models are going to be disrupted. Machines are going to break more often.
I just wanted to add, Chris, that if you find those cloud machines that err more frequently and in fact stop, especially the fail-stop failures, we'd like to know about them. The problem is, since about 2003 or so, we have been doing work on fault tolerance in my group. And every time we said petascale machines are going to fail very frequently, whatever. And so, and then there is another component in the field, another group of people that say, no, engineers will fix the machines; they will never fail in time for your simulations to finish. And so we developed this research. And in fact, right now we have, like you heard from Xiang, this automatic system that if a job is running and one node dies, it will automatically. And in fact, we should have brought the small cluster of these beagle bones here. You could actually just plug out one of those things and it will keep running. So we have those nice schemes there. We just don't have a good place to run them on because we don't get failures enough. We have to plug things out, inject failures, whatever. And clouds may be a very nice test environment for that then.
So just a quick note. You're perfectly right. It's Beowulf all over again, right? We're building from off-the-shelf components, and they have much higher failure rates. But we don't really know how high, right? So we don't really have data from those big cloud providers saying, you know, this is what happens. This is how often we fail. And to speak to Sanjay's appeal, right? If you find the failures, let us know, right? I actually looked at different papers to see if somebody has reliable data on that, and not so much. And so I started talking to Google, and I started talking to various cloud providers about making such data available. There is actually a group that I'm participating in founding called Open Big Cloud that will have a workshop next week, and that will bring together people from both academia and industry, and primarily industry, really, to look at extreme phenomena in the cloud, right? So look at big compute in the cloud, look at big data in the cloud. And what we cannot do right now is look at those things very effectively because we simply don't have the data, right? Because a lot of the cloud providers don't share the data. But yet, you know, fault tolerance and reliability is one of the hottest research topics, I think, in the cloud for the very reason that you mentioned, right? If you're going to provide a reliable supercomputer, you need to know something. And so I think that the place to start is having the data.
So if I may add a couple of things. Someone made observation that things can fail quite a bit in the cloud. That is true, but that's really the question of scale up versus scale out. And I think the industry has more or less decided to go scale out for two major reasons. The first is cost, because it's much cheaper to go scale out than to develop high-end machines. But the other frequently overlooked reason is the scale. You know, if you look, but that has to be qualified, scale for certain applications. So most of the applications are now designed for scale out, and they go, you know, over hundreds of thousands of nodes. And you cannot afford these kinds of machines for the scale up, these number of cores and memory, etc. And however, to overcome the issues of the failures, one moves failure tolerance at the higher and higher level. So as Roy was pointing out, the disks and machines and servers fail. No one bothers to replace them because either storage or the applications or the servers. For web servers, it's trivial, but many, many more applications are just being designed to tolerate these failures.
I think also you raised a very good point on the issue of economics. And one of the things you say in terms of the type of problems you're trying to solve and how they deal with economics, you know, there are certain HPC problems that I call, as long as the result fails to suck, it's good enough. And if you're simulating the Big Bang and like the 1 second to 1,000 years after the Big Bang, and what you get is universe-like, then you're satisfied. You can have all kinds of errors inside, and it's good enough. There's another class which is the needle in a haystack problem. Let's say you're looking for the DES key, or you're trying to find a hash collision. As long as the errors occur on straw and not on the needle, you're okay. And then there are the third, more unfortunate times where it's perfect, where you're factoring a number, doing a probability proof as an example, and where a single bit error, you know, wastes the entire calculation. So sometimes you might be able to handle the cloud by trying to move the kind of questions you ask over to the it fails to suck as opposed to it's got to be perfect as a way of handling reality, which is messy. It'll cost a lot less if you have the first rather than the last.
While I wait for the next question, I just want to tell Landon, Blue Otter, one of the most powerful academic computers in the US, refused to participate in the top 500. No top 500 entry for Blue Otters.
I was a system programmer for ILIAC 4, and I'm glad that somebody actually got to use it for something useful.
Hey, how do you know it was useful?
Right, yes. But one of the big changes between then and now, ILIAC 4 had a 1,000-bit wide memory I/O bus. Spit 1,000 bits every second, every microsecond. It was, the skew on that is sort of amazing. But they made it work, I think. only for 16 processors. But and back in those days, for supercomputing, they didn't seem to worry that much about, in some ways they didn't worry about reliability. You know, Seymour Cray said parity is for farmers. He's not going to slow down his machine by doing any parity checking. And he's going to have a 60-bit word, so he doesn't have to do any really fancy floating point arithmetic. And I think some of his machines didn't even have a divide.
Yeah, well, the early Crays just had a reciprocal approximation unit. And when I did the Merce-N prime test on the first Cray 1, I didn't get the right answer, and it turned out there was a bug. There was a bit error in the lookup table, and at serial 13. But there's a lot of physics code that was written for the previous machines, and if you went and fixed the hardware, you broke the code.
Yeah.
Right. And then there was machines that were not serial numbered but were in a TLA, and they were trying to do stuff, and they had to decide do they want the fix or not the fix.
Right.
So it's errors in classical computing is theirs, but again, I think HPC is trying to solve problems that are bigger than one machine can handle, that last longer than one machine will correctly compute, and will produce more data than what one convenient little storage pod will have. And so when you're dealing with those kind of problems, you're just trying the way to work it. In the case of the iliac, it was use maybe 2 pods of 16 and vote and retry when you got an error, rather than assume you get slightly faster by assuming all the processes work perfectly all the time.
Right. Yeah, we the Coordinated Science Lab got a CDC 1604, is that the right number?
Yeah.
And they emulated iliac 1 on it, and to test their emulator, they ran the hardware check paper tape through, and they found an error in the CDC hardware.
Sure, and so we one of the excuses that number theorists have in looking for doing like computational problems is we do hardware checking, right? If you have a perfect problem, I mean, this is a thing. If you want to get time, get idle time on people's machines and check out their hardware and help them report hardware bugs, OS bugs. Do you think that the virtual machine is going to always swap in the right page of memory? If you're not marking your pages of memory and looking at them occasionally, you'll be disappointed. So build fault tolerant code, and I think Charm++ has the ability to not only schedule the right resources, but say that thing seems to be kind of giving us too many wrong answers. Let's avoid using that node and move stuff elsewhere.
Right. But it strikes me that nowadays, with things like Thunderbolt to connect that are very fast, you could end up almost putting together a network that satisfies the way your data exists. Yeah. Since you don't need a memory bus, or we're getting so fast we don't need memory buses, and that sort of just changes everything.
I was going to say that I think if you push the envelope, you'll always run into the reliability problem. And so nowadays what we have to do is to build machines or build architectures, build software designs that encompass reliability, because you can't just be guaranteed that the underlying system gives you that.
And of course, unfortunately, if you're actually doing something interesting, you're pushing the envelope. Yeah. And that's what research is. So you just assume the universe is not very perfect, and you just have to live in that universe.
I think what's interesting about COTS is they start out believing that their universe is not very satisfactory. Sometimes we make the assumption if you spend a lot of money, you get something that actually works, which is a big mistake.
So I don't have a question, but really a comment to drive discussion. So many years ago, I'd heard about this cloud thing, and I was like, I don't know what it is, right? And then I have to write an NSF report, and they said, well, you're getting all this computer time. What's it worth? Okay, I got 2 million hours on XC. What is it worth? Because they want a dollar amount. The NSF, like, what is it, right? So, okay, I used the cloud. I went to Amazon, and I looked up something appropriate, and at least it gave me a price, right? So I'm like, okay, but I guess people run here in the HPC, in the cloud, because they offer this service, right? So then a few years went by, and I've noticed 2 things. So I'm a university researcher. For my PhD, I used many supercomputers, writing codes. These are these very regular machines like Crays. And then I got out of the business for a while, Now we're trying to hook up with Charm++ to write applications in a different way. But from a researcher at a university viewpoint, here's this computation I want to do. I could try to run it at a national supercomputing center. They are severely underfunded, so I get about 1/6 of my compute cycles I use each year in the national supercomputing centers, although I'm 100% funded by the federal government.
Yeah.
Okay, so what am I supposed to do with myself? So luckily, the provost at my university has decided to spend money on computers. Okay, so they have a big cluster for a university, and I get just access to it, and I just suck up all the cycles, and as you say, steal cycles that are just sitting around. So we get our work done. But this is a very expensive proposition for them. They're going to probably start charging user fees. And we will never be able to pay this from our grants because the federal funding is at most stable, but probably decreasing. So they're just going to squeeze us. Where are they going to squeeze us? I don't see any other place than telling us go buy cycles from Amazon or something like this. I'm just trying to have a very pragmatic view of the pressures on a university researcher with the dwindling or fixed at most funds, insufficient national resources, and a university system that will fundamentally push you out because it's too expensive for them.
One of the things I think that you want to look at is try to get them to get job schedulers, resource schedulers that can handle background tasks and say, okay, I've been granted this much money, this much time, but if there's extra time, let me come in and backfill. The other thing
they want to charge me money for that.
Yeah, the other thing is try to show if you're going to be contributing to the heat death of the universe, show that along the way you're contributing value is another way to handle it.
I like that, heat death. I think what you described is a really big problem for all the universities and for probably lots of other research institutions too, that there isn't that much spare cash in the economy. And if you look at the economic cycle, there's going to be a downturn in a couple of years, and that's going to hit us really bad. So you need to plan for that. Actually building systems for universities that provide you critical infrastructure, if you like, for your research, but do not cost an arm and a leg, and sort of take all of the best demonstrations out of the cloud industry and apply them to the way you're providing those facilities, I think is something that we should all be learning how to do. You shouldn't be having labs with different machines in a university. Maybe within the big 10 universities, we should be sharing one huge computing infrastructure. And perhaps we should be organizing that computer infrastructure so it's simple enough that there's only a couple of people actually managing it. We really need to rethink how we're providing those computer facilities, and maybe we don't need 90% utilization of those machines, but what we want is a really low cost 70, 60 something percent. We need to find that out. And this is one of the reasons I like Charm so much, is that it's flexible enough that you can play with the infrastructure and still write your codes, still get your codes to work without binding it to a particular infrastructure. You can get the infrastructure adaptive to what you're trying to do.
I just wanted to say, for a while I thought about this. National centers serve a couple of different roles. They provide cycles. They also provide consulting and expertise. They are reservoirs of expertise. That second function, if you can separate it, refactor it, then if you think about cycle supply, then the one way in which NSF and other agencies could deal with this is by basically not funding cycle providers directly, like TAC or Texas or Waters. What am I saying here? But anyways, okay. But in some future world, but then directly, then just give people money for compute power, and then they can buy their compute power from whatever provider they want. And IBM, Cray can build their supercomputers and charge on per use basis. What interesting things will happen once this is a market like that? Well, jobs that don't really require tight coupling will go the cheaper route. Jobs that require, even within supercomputers, I believe there are maybe 2 or 3 separate categories of applications and machines, like the ones that require bisection bandwidth, full bisection bandwidth versus the ones that don't, ones that require a lot of memory per core versus some that don't, and the market will choose and apportion resources between these different types of computers correctly if we were to do that. I think that will be an interesting thing to do. I don't know the funding agencies will go that way, but.
Okay, just a one small point to pick up on things that others said earlier. One thing to realize about the resources in the cloud is that they're on demand. This is a very significant difference from what typical computational center gives you, which is batch access. And so the point that was made before about let's find a way to run in the background, well, cloud providers provide such a way for much cheaper than the on-demand cycles, and Amazon, for example, calls it spot pricing, right? That means that you get resources that are somewhat volatile. You don't know when they become available at the price you want or when they will be yanked away from you, but you pay hugely less for them than you do for those on-demand resources. And that goes back to Sanjay's point as well, which is that market will find the price. You don't need really powerful resources for every single computation. Market will find the price for resources that are maybe not as powerful as others might require, right? But that goes not just to the shape of the hardware, but also to how that hardware is made available to you.
And Cisco, I won't name them, but Cisco has a large cloud providers building stuff with our equipment and our computers. And one of the things that this cloud provider is going to be that power is also power and cooling, which means if you're an HPC job and you want to rev up the memory and use lots of cooling stuff, you're going to get charged more than if you're a job which is gentler on the CPU. So one of the things that Charm++ could help someone do is to not bang the CPU quite so hard. Your error rates might be better, but also your power costs might be better as well. So working on power consumption as a property, as well as error recovery, is something that I think Charm++ can give people that ability to let the computer scientists help the scientists use the hardware.
In fact, there was a talk yesterday on that, and we have quite a bit of work on that. So I suppose cloud would be a good place to test those ideas with optimal allocation of power and energy for temperature and cooling. Yes.
All right. So you guys were talking about fault resilience, and we need to build it into the algorithms, and that sounds wonderful. Charm, it has some capability in that respect, but it's still at a very coarse level of, yeah, this node went down, at which point, yeah, you can tell it. For your prime factorization, you have a way of testing, did I get the right answer? But if I'm solving some nonlinear PDE, how do I know if I'm getting the right answer back?
This, of course, is a hot area of debate within HPC now. And say last week at Solution conference, there was quite a bit of discussion about it. But there are several ways. One is, for example, if you have some kind of a field, then an error in one place in that field is going to only delay conversions. You can do it, think of it that way. So make algorithms that tolerate small failures that way. And the variables that are kind of important, we'll store them in some reliable way, maybe 2 copies or something like that. The other alternative was some multi-grid like approximation. Suppose you have a field type value again. For every point in space, there is some value. Well, represent a reduced representation of that for every 8 points or for every 64 points. Put an average value there, and then see if any one of them are significantly different than that after every checkpoint. And that will tell you something went wrong here. Then you are going to do some approximation to the outlier, and that will maybe again have some impact on convergence. But there are methods of this sort for values that are just generally describing some floating point field over space, for example.
I think Dejan had some points regarding them to say something.
Well, I actually had for the previous. I don't want to interrupt this discussion.
No.
Well, the previous question was around whether you do it in the cloud or buy equipment. And interestingly enough, when we were building OpenCirrus and we bought equipment for UIUC, Indy Gupta and I have done analysis of, was it the good idea to buy the equipment, or were they supposed to go to Amazon? And the answer was simple. It is all function of the utilization. There is always a break-even point in this spectrum. To one point, it's better if you, for short-time use, it's better to just go to Amazon. But if you're planning to use equipment for long-term, then it's better to have your own equipment. And utilization moves that earlier or later. If you are utilizing it heavily, then that break-even point comes even earlier, and you should buy your equipment earlier. It's a very simple math.
I do have a rider to this, which is I think one of the things that we need to be able to do is be agile in our HPC, in our computations, and so on. Everything's changing. Even the way that we think about data and its interaction with our computations. So we've heard about collecting huge amounts of sensor data and putting that somewhere. Well, we don't know how to do that, really. We're starting to do it. We've got Storm, we've got all sorts of other things, but we don't really know how to do that. What we need to do is be agile, and we need to be able to adapt. And one of the things that the cloud technology brings to us, even if we don't like to admit it, is that it's designed by people who get, perhaps one might say, poor programmers, but certainly not really sort of top-notch HPC programmers, but they're doing things in parallel, computing things that the companies, whatever, need to be done, and they're doing it very efficiently. If you take Amazon and you try and implement your own algorithm on Amazon, you're likely to cost yourself a lot of money because of the mistakes and the time that you use in trying to get your algorithm right. Having a local machine is a lot cheaper, but also having the right software development techniques would be even better. So I really would think one of the keys to all of this is to build your software development so you can change your mind, so you can be adaptive, and you can move from one platform to another.
One of the things on terms of reliability and simulations, that's doing something like you're simulating Jupiter. I try to simulate more than one Jupiter with more than one algorithm, because more likely the error is in my code, not in Jupiter. And if there's like CPU errors or something, you might see that one of the three simulations has some spots where you can sort of outvote or retry that area. But that's another example. You have to use more resources in order to gain greater perfection, but that's what the universe has you do.
I wanted to pick up on the point that Roy made and that Sanjay also made, which is that clouds are a disruption, and they are disruptive in the sense that they renegotiate the roles and the established tools that we have to accomplish things. So one thing is, when you go to Amazon, you're buying not just the resource, but you're also buying certain types of maintenance of that resource, right? You're buying the floor space, somebody to maintain it, keep it running, and so forth. But on the other hand, you're not buying what you used to get from computational centers, is somebody to configure the resources that you're running, right? And this is now something that you have to either provide yourself or create a new layer of system administrator or a new layer of services that will be operating within your institution and providing those things. We don't, right now, those boundaries are not completely clearly understood, and we don't have things that do those things. The other layer, of course, is the software, right? How do we deploy those virtual clusters reliably? How do we adapt to failures by redeploying more machines, for example? How do we contextualize those virtual machines so that they securely find out about each other and can operate as one unit, and so on and so forth? And unless you have that software, you will spend a lot of time developing, and not just a lot of your effort time, but also a lot of the time that you're buying from Amazon to run those things. So, while cloud computing provides compute power on tap, at this point in time, it sometimes seems like every time you want to turn that tap, you have to call a plumber, and that gets very expensive. And this is a cloud computing issue right now. It's not just HPC in the cloud computing issue, right? This is very widespread. So solving it would amortize pretty quickly, right? Would have benefits for all sorts of applications not just the HPC applications.
So interestingly enough, I've heard different perspective about ability to reconfigure, and that exactly came from the national labs, that with big supercomputers you can't really touch and reconfigure anything. If you do it in the cloud, you can make changes to your virtual machine, you can put different kinds of libraries, play with it a little bit more. But otherwise, I agree completely that the future will really rely on how we program and use these massively parallel hardware architectures. So new programming models, new algorithms, be it for Jupiter or for other planets or universe, I don't know, but
sure. Well,
outside of my scope.
And you also raise a good point. I mean, Cisco has put a lot of effort into its UCS product, its computer product, and we built computers part because we thought that one of the places you can put the brains is pull it out of the kernel and into the network, and let the network control the computers. So part of the thing is, as well as we have customers that spend a lot of time just bookkeeping, keeping a spreadsheet of all the nodes and who's doing what and so forth. That's a non-trivial amount of time. So trying to allow people to have generic machines that the network can configure on the fly is much better. You build a data center by wiring it once and let the network redefine your set. Now that comes with a cost, but the value, if you're talking about amortization, economic value is much better. And the people who understand the total cost of computing, or if you're a researcher, the total cost to your grant, will appreciate a machine that's easier to reconfigure, easier to administer, and easier to manage.
And I apologize, I will have to leave now because I have another conflict with the meetings. Thank you very much for having me here.
Yeah. So.
Thank you.
Bye, Dejan.
Bye.
So just a quick note, I think that we all agree as to that. So half of the users I work with tell me that they want to configure their own virtual machines, and the other half tell me that they don't, right? And this is not really a contradiction. They all would like to have as much control as possible over the resources. It's just that some of them do not have the skill and expertise to configure them themselves, right? So, right. So what's really needed is somebody who can work with them on that. And yes, it used to be impossible to do that in large computational centers. They always had to strike a balance in the environment that they provided between various conflicting requirements of users. And when you have a virtual machine, you can do that much more easily, but you still need that support.
Yes, I mean, so I should. So what you said reminded me of a operating system. You need some reconfigurability stuff happening depending on what the users want. I think it was also start with CH. What was it? Choices. So I did a thing called choices, an operating system. And I think I would like to personally, although I know we are running late now, but the US NIC we talked about commodity. Components being used more and more in HPC. Dejan made a point about only a few people can have these white elephants, but majority are going to have systems built using the commodities. And in fact, I was very impressed with the US NIC. I don't know how public those results are, but maybe you could tell a little bit about that.
Thank you for that sales thing. I'm not a salesperson, so you have to sort of prompt me to do it. But Cisco has some interesting networking technology where essentially it allows for processors to directly control the network device rather than. And so we have these network cards where you can have 256 virtual Ethernets, right? And depending upon what PCI addresses you talk to, Ethernet A, B, or C. Well, by bypassing the kernel and allowing a user process to directly map into that memory, a user process can directly send and receive a message and get very, very low latencies. And then by doing that double bypass through a hypervisor, you can have jobs running on a virtual machine, running on a hypervisor, talking to a slice of hardware that then builds, can perform their networking. But these kind of virtual hardwares, virtual Ethernets, allow people to build networks based upon what they need. The old classic ways, you've got two Ethernet cards or two plugs, and so you put this stuff on network A and this stuff on network B. When you have these virtual networks, you can say, I need a network to do my administration. I need a network to launch jobs. I need a network to do backups. I need a network to do telephony. I need a network to do MPI-like things. And you can build your networks on the fly, virtual networks over the Ether network quite effectively, so that you're in control of how your network's configured rather than the hardware's control of you, or at least it minimizes it. But the main thing about USNIC is its ability to essentially have processes directly send and receive messages. The next generation of NICs are going to have even smarter processing going on. I'm not allowed to talk about that, but you can imagine doing some more intelligent things in the actual network devices can accomplish stuff.
You may not be able to talk about your stuff, but I can certainly talk about SDNs. You're going to see a network revolution going on, and we're going to make networks a service just like everything else. So if you want some fancy network, you can just design it with software. This is just around the corner. So this is all very exciting. I'm not sure how you program it in Charm++, but I'm sure at the next meeting there'll be probably somebody saying this.
So if I may interrupt, we are running late, and in the interest of time, we'll have to end the session. But I'm sure you have lots of other questions, and we can ask those questions during the break. And let's again thank the excellent panelists.